Hi, and welcome to the third episode of Experts and Experiences. I'm Tiffany Liu, Internal Vice President of Blockchain at Berkeley.
And I'm Brent Friedman, Head of Education of Blockchain at Berkeley.
We're delighted to be back as your hosts, bringing you closer to the visionary founders within the Berkeley Blockchain Accelerator, the premier university blockchain startup accelerator in the United States.
Blockchain at Berkeley continues to drive innovation in the blockchain space, offering practical education, conducting cutting-edge research, and delivering consulting services to leading enterprise companies.
Today, we're privileged to have Levi Rybolov, the founder of CoopHive, joining us. Hi, Levi. How are you doing today?
Good, how are you?
Good.
I'm doing great. Could you please introduce yourself a bit and your role within CoopHive?
Yeah, so I'm the founder of CoopHive, and CoopHive is a two-sided marketplace for compute that we're using as a coordination layer for decentralized intelligence. I got my start in distributed computing, in particular game theory for distributed computing, back in 2017. There was a crypto bubble back then, and I started looking at all these cryptos, and I was like, oh man, that looks like a lot of wasted energy. It can be doing any better than that. And I got attracted to this cryptocurrency called the Gridcoin, which was the 20-something coin ever created. And it was designed to incentivize contributions to the BOINC distributed computing platform. So BOINC grew out of SETI at home, which was the search for extraterrestrial intelligence at home. So basically what people did was some scientists, they got signals from various sources, and then they sent data and compute to nodes around the world to process it to look for aliens, basically. And out of that grew BOINC, the Berkeley Open Infrastructure for Network Computing, which was the same principle applied to like any scientific computation. So any scientist could come along, make their own project, and distribute computational workloads to volunteers around the world. And so that's how, I thought that was a much better use of the energy. And so I got very interested in the incentive structures of the coin. A couple of years ago, I published a paper on the topic, and then later that year, I was recruited to work on the Bacalhau distributed computing platform, which was a computing platform built at Protocol Labs, designed to have native IPFS ingress and egress, as well as bring the compute to the data rather than the data to the compute. So you could imagine if you have like a 10 terabyte data set that you want to run computations over, it's much easier to send over the computations in whatever relevant format you want, probably maybe a Docker image, to where the data is, and then compute the result locally, and then send back the result, rather than trying to transfer those 10 terabytes of data. And then so I was working on that, and then we, out of that work grew our work on building an incentivization layer on top of Bacalhau. And we had a contract for that last year. And then in January, a couple of months ago, we got spun out from Protocol Labs. So we were effectively incubated there, and we just got spun out. And they provided us pre-seed funding, and now we're working on a lot of really cool stuff.
Yeah, that sounds great. First, it sounds like you're very knowledgeable in the space based on all your background. Can you give us like a brief overview of a little bit about the product?
Yeah, so basically, CoopHive is a two-sided marketplace for compute at its core, and I'll get to, maybe at some point I'll get to how we want to generalize it quite a bit. But for now, it's a two-sided marketplace for compute. You have clients on one side, compute nodes on the other. Each of them have job and resource offers. So like the compute node can offer up, however many GPUs and however many cores and however much RAM it has. And then the client may have a particular computational workload they need done. And so they send as of right now, they send their request to a solver, which is an intermediary node that basically acts as a market maker. And it matches a bunch of job offers and resource offers from many different sources. It proposes the match to the two sides, the client and the compute node. If the two parties agree, they sign a deal. The deal is put into an IPFS CID, and the CID is put on chain. So what that basically means is we only actually really carry the IP, the hash of the data, plus some any other relevant metadata that we need to have on chain. But really, it's really quite lightweight. We really try to only store the hash on chain. So the hash of the deal is stored on chain. The compute node computes the result. The result is also put into an IPFS CID. That CID is also put on chain. And then there's an optional mediation process. And if there's a mediation process, again, the results of the mediation process are put into an IPFS CID, and the CID is put on chain. And so what we effectively end up with is a sequence of IPFS CIDs that have particular rules around governing how they're put on chain. And so this is a very, very lightweight data structure, because you basically just have some set of rules defining how you put IPFS CIDs, really just hashes on chain, and those hashes are pointers to off-chain data. So it is very minimal in its structure, and that's why it's able to do. You can use it for many different purposes.
So would you say then that this is kind of like an optimistic protocol then, in the fact that you said there's a mediation process, and I guess like when is that mediation process triggered?
Great question. So we were originally tasked with, or in particular, I was originally tasked with, because I was doing the game theory, I was originally tasked with finding ways to prevent cheating in this network using purely optimistic compute, or verification via replication, meaning that the only tool you really have to determine whether a computation was done correctly is by completely recomputing the result from scratch. So no secure enclaves, no interactive proofs, which means no zero knowledge proofs or anything like that. No multi-party computation. The only tool you have is completely recomputing the result from scratch. And assuming the result is deterministic, and that's quite hard, but we set that to the side for a moment. Assuming that the result is deterministic, how do you prevent cheating in the network? And so I do want to mention that that was what we were originally tasked with. However, we can relatively easily incorporate, and it is on the roadmap, incorporate other verification protocols like zero knowledge proofs, and use have capabilities for secure enclaves and so on. But to get back to the optimistic stuff, when is it triggered? So that is a really good question. So first, as of right now, it is decided by the client when to trigger it. And so there's no set rule that the protocol enforces. It is a choice of the client whether or not they want to. And the client has to take many different factors into account when they're deciding whether or not they want to replicate a job, and how they want to replicate a job. It's worth pointing out that the issue of preventing cheating in distributed computing networks ultimately boils down to preventing collusion in distributed computing networks.
Mm-hmm.
The reason that this is the case is because the way that you fundamentally check whether a result is done is by running the computation on another node. And so what you have to be concerned with is whether that node is being honest or not. So in the case where you're using a trusted third party to do the computation, then the math for staking and slashing and how often to check is actually very trivial. But when you're working in a totally, and when I say trusted third party, I mean that like in the cryptography sense of it's practically an oracle, you're going to get the right answer from it, and so on. So the question is, in environments where you don't have a trusted third party, what do you do? And that becomes quite tricky, because now the nodes that are acting as mediators can collude, right? So what can go wrong here? So the client can come up, sorry, the mediator can go up to the original compute node and say, listen, I don't really care whether or not you did the computation correctly. I don't really want to run it because it's going to cost me. And so instead, why don't I just give back the same result you gave, and you give me a portion of what you get paid, right? And so that makes the protocol insecure, because now the mediating nodes are not actually checking the result that the compute node provided. Likewise, the mediating node can come to the client and say to the client, hey, I actually don't really care whether or not the compute node did the result correctly. I'm going to say they did the result incorrectly. And you and I can simply split the collateral that they put up to guarantee that they wouldn't cheat. And so that's another form of collusion. And that's basically only in the case with 3 parties. You can imagine it getting a bit more complicated when, if, for example, you have a consortium of mediators, rather than just a single mediator. Although under some realistic assumptions like majority honest nodes, it can become a bit easier to work that way, actually. But yeah, so that's kind of the DL on how like verification works.
Okay, got it. So I guess that kind of leads me into my next question, which is like, how are compute nodes and mediator nodes incentivized to work on the network?
Oh, they're paid by the client.
Oh, they're paid by the client. Okay.
Yeah. This is it's a two-sided marketplace for compute. So they're if they're getting paid to run jobs, basically.
And what are some ways that you mitigate the effects of the collusion or the insecurity in the network?
So in the for now, we have capacity for basically a consortium of mediators to run the verification. And so that basically means is a group of nodes come together and compute the result, and then decide on what the outcome is, and that's basically used as a mediation protocol. That's optional. The issue of preventing collusion itself, so the approach that we are taking is an adversary first approach. So basically there are, and we have to kind of do a bit of a kind of side tangent on a bit of game theory stuff. So basically there are a lot of assumptions in game theory. So I guess there's a few different topics to cover about what we have to talk about. So one is so we're using computational methods, simulation-based methods, empirical methods rather than analytic methods, right? What does that mean? So we're not trying to come up with a closed form solution to the problem that will tell you exactly how to run the protocol and basically give you a formula for how to do it. The reason being that when you remove the assumption, like even one assumption that you put into that protocol, a lot of your guarantees break down. And it's almost impossible to define the environment of the protocol in its full generality. So that is one reason why we're not going for analytic solutions and we're going for simulation-based solutions. Now, there are other reasons as well, which is that a lot of game theoretic literature assumes that agents are utility maximizing, meaning that if they can cheat, they will cheat. If they can collude and it benefits them, they will collude. And we know that in the real world, humans are not rational. And this is a major, and even if they are rational, how do they know what the right decision is, right? They have to know whether or not it would be logical for them to cheat or not. And then on top of that, they would have to execute the cheat in the perfect manner, basically. So there's a lot of ways that like kind of traditional game theoretic approaches to this problem break down. And so the approach that we're taking is an adversary first approach. And what that means is that we're going to be training agents to represent clients and compute nodes, and the purpose of those agents is to maximize the utility on behalf of their owners. And so you basically want to train these agents in this environment to maximally extract value from it. And then with those agents in mind, you want to build your incentive structures to be resilient against those kinds of attackers. Now, I want to give a couple of caveats here, one of which is that we're kind of using like a multi-agent reinforcement learning here, kind of multi-agent inverse reinforcement learning. And we know that these protocols are not necessarily guaranteed to converge to equilibria under probably under the conditions that we're in. So this is not a foolproof method by any stretch of the imagination. So the kind of the way you should think about this is that this is a kind of like game theoretic white hat hacking, basically. You basically want to create the strongest adversary, the strongest opponent you possibly can, and then optimize against that. That's kind of the big picture heuristic approach that we're using.
Okay, got it. I guess one more like kind of technical question I wanted to ask. I think you mentioned like early on that obviously if you're having clients that want to propose computations to these compute nodes, there's a lot of data transfer that might need to happen. How do you mitigate like the data transfer? I think you mentioned something about Dockerization.
Oh, so yeah, basically you want to use a paradigm. Most of the time you want to use a paradigm called either compute to data or compute over data. And what that basically means is that you locate where the data, you find where the data is located first, and then you send the computations there. So if there's like 5 places where this 10 terabyte data set is being stored, when you send out a job to the network, ideally only the nodes that actually have the data can bid on the job, basically. That's kind of how you do that. And then assuming that they do have the data, if they don't, it's another story, but like there's ways of like preventing that game theoretically. But assuming that they do have the data, they bid on it, and then they're matched in the market, and then everything proceeds as usual. So the data does not move. And just the description of the compute that you want, for example, like a Docker container, that is sent over to where the compute is, and that's where the compute is done.
Okay, that makes sense.
Okay. Now we kind of want to dive into the users. So who is CoopHive designed for? I know you said there's the clients and then also the computers who are storing the data. So like are these usually just individual programmers or like companies themselves?
It's a great question. So we're focusing primarily on scientific computing. That is mostly because of kind of my interest in the space and my background in the space. Who's using it? So that's a really good question. There are a number, because of the flexibility of this protocol, there's a lot that you can do with it. But we're basically aiming for enabling scientists to have decentralized provenance and reproducibility over scientific computations in a kind of decentralized distributed manner that blockchains provide. So you can imagine, and going back to the SETI at home example, they were sending out all of these scientific workloads to be done all around the world, and then people got credits in return. And so when people got credits, they basically they weren't transferable. They were just like these kind of internet points, basically. But you can imagine, for example, tokenizing those points and those rewards, right? Actually giving value to them, and then now that you have a token and it's fungible and it's tradable, you can put it on markets and have it be exchangeable with any other. Let's say you put it on like Uniswap or whatever, now you can exchange it with any other token. And so the price of the token effectively acts as a prediction market for the value of the computation. And so what this protocol can do is effectively enable the utilization of latent computing power for kind of beneficial purposes, right? So you can imagine, for example, let's say someone thinks they have the cure for cancer and they need a lot of computing power for it, but they don't have the money. This protocol is designed for computations that nobody is willing to pay for now, but that somebody might be willing to pay for later. Or this is one way that we're focusing on it, right? And so what does that mean? It means that person that thinks they have the cure for cancer, they send out their computations to all these compute nodes. And then, if in fact they do find a cure for cancer for this, there's a verifiable trace over who contributed what to the protocol. And you can retroactively reward nodes either with things like IP NFTs or retroactive public goods funding, depending on what exactly the situation is. And so, it basically, one use case that we're really interested in is enabling scientists to access, massive amounts of latent computing power around the world to basically like kind of do really cool stuff and like just make new discoveries that they wouldn't have been able to because they didn't have the resources before.
Cool. I guess, are there any competitors in the space, or would you say that CoopHive is kind of like a newer product? And if there are competitors, are there any unique aspects or functionalities that set CoopHive apart?
So I would say on what we're particularly focusing on, no. The most of the compute focused protocols are focused on different things. Like, I mean, of course, AI has recently become a very hot topic, and we can run AI workloads, of course. I mean, we can run kind of like Docker containers in general. But there's nobody really focusing on the very like a niche thing that we're focusing on. Probably because they probably will be soon. But there's been so much hubbub around DePIN and decentralized AI recently that decentralized science has kind of not been getting as much attention. So there isn't anybody doing like focusing on the precise use cases that we're working on. There are other competitors in general, other distributed computing platforms, but and there are a few that are close, but there are none that are doing like precisely what we're doing. And furthermore, we have pluggable our executors are pluggable, so we can really plug into any other network and run jobs there as well. So we're very, very collaborative and very love working within the ecosystem with partners, basically, because we are, at the end of the day, we're a marketplace that we're using to coordinate systems, right? So we're not about like only our token, only our network, only our protocol, et cetera, et cetera.
Yeah, for sure. Can you provide maybe an example of a partnership that you've previously have, or like any business that integrates with CoopHive and your operations?
So we just got spun out. And so what that basically means is we are forming the team right now. So we do have some strong partnerships, let's say in stealthish mode. I want to kind of keep it there for right now. But yeah, so we have some very, very exciting stuff cooking.
Okay, got it. So I noticed on your website that you said that it's a multi-chain. It integrates with multiple chains. Could you elaborate on which chains are integrated?
Yeah. So we can basically, because we're EVM compatible, we can run Rady on any Solidity-based chain, or any EVM compatible chain. Our first focus primarily is on Filecoin and FVM and IPC. The main reasons being that we were incubated at Protocol Labs, and a lot of our thinking and our design was centered around these, computation over these data sets that are available on the network. So that's primarily where we're focusing our efforts. But in principle, yeah, we can deploy to any EVM compatible network.
Yeah, that sounds great. Could you maybe walk us through the typical life cycle of a job within CoopHive, from the initial submission by the client to the final delivery of the results?
Yeah, so the clients and the compute nodes all have job and resource offers, and those are basically descriptions of hardware requirements and job requirements. And those are sent to this intermediary node called the solver. The solver then does some market making algorithm, and to be clear, you can have pluggable. You can have more than one solver, so you can have a solver as a service, effectively, right? Whoever performs the best market making, will become more popular, effectively. It's a kind of a free market of market makers, and so the solver does whatever their matching algorithm is, and proposes for every match that it finds, it takes it proposes that match, the details of that match, to both the client and the compute node. Both the client and the compute node consider whether or not they want to do it. If they do, then they both sign transactions that basically and they put collateral in escrow. There's different types of collateral. They put the collateral in escrow to basically guarantee that, like, for example, the client will put up collateral to guarantee that the compute node can get paid, and the compute node can puts up collateral to guarantee it won't cheat. There are more than those types of collateral, but those are examples. And so they basically sign the transactions. The deal is put on chain. They post the relevant collateral. The compute node goes and runs the job. It gets the result. It puts the result into an IPFS CID. The IPFS CID is put on chain, and then there's a period of time that the client has to challenge the result, basically, or check the result, whether or not it was done correctly. So if the client accepts, then it basically, everything's good. It retrieves the data, and the job's lifecycle is done. If not, then the client can trigger a mediation protocol. If there's a mediation protocol and the client is found to have cheated, then their collateral is so if the compute node is found to have cheated, their collateral is slashed. It's distributed among the nodes that did the mediation and the client in a kind of really in an arbitrary manner. If it was found to have not cheated, then basically the mediating nodes get paid by the client, and then the client gets their result like they did before.
Okay, got it. So just to clarify, I guess, so like let's say I'm a client node and I have to define the requirements for the hardware needed to perform a certain computational task that I'm submitting as a job. If I somehow incorrectly define the hardware needed or something, or incorrectly define my computation and submit it to the network, and then a computation node tries to undertake that computation, but obviously fails, what happens in that situation?
But can you elaborate on what you mean by it fails? Yeah.
I guess like the job is incorrectly defined, and as a result, the computation isn't able to be completed by the node that it was assigned to.
Got it. Yeah, so it depends on what type of error occurs. Is it like, like seg fault type error, or is it like halting problem, like this job never ends type error, or is it like some kind of just like yeah, so it depends on the type of error. The way it would work, but at the end of the day, the way it would work is that this is also why in principle, the compute node should also be able to check to call upon a mediation protocol as well, because of potential attacks from the client. You really kind of want anybody to be able to call upon a mediation process, and the mediation process is what determines the payment flows. So regardless of the job description being correct or incorrect, or the result, it ultimately depends on what the mediating nodes say. If the mediating nodes because if they also all fail to do it, then they know that the compute node was being honest, and that the client kind of just did kind of an incorrect job submission, basically. But like, that's just like kind of whatever. The compute node still did the job correctly, so it doesn't matter.
Diving into kind of future directions, what's the current stage of your product, and are you in the process of raising funds right now or in the future?
So we are building right now. We did get pre-seed funding from Protocol Labs, and we're using that to hire and build out our protocol. We will be raising soon.
Okay, got it. And are there any upcoming dates or releases that people should be aware of at this time?
I can give a couple of dates that are relevant. So I mean, for example, I'll be at like DCI London this weekend, and then I will be at the Berkeley events for the accelerator and the RDI Center for Responsible Decentralized Intelligence, and Funding the Commons / Earth Commons, and Lab Week for Protocol Labs in San Francisco in mid-April. That is where I will be doing a lot of stuff. I would say watch out for announcements around that time.
Great. Do you also have a waiting list or a mailing list that maybe listeners can go to stay updated with these releases that you have upcoming?
Yeah, so you can go to coophive.network, CoopHive.network. And there is a waiting list button there. You can click and submit your information. You can also feel free to reach out to us directly, hello@coophive.network. Yeah, those are, or DM us on Twitter or on Discord.
Perfect. Well, is there anything else you'd like to share about CoopHive or its vision for the future?
Yeah, maybe kind of a few things. So, one thing that we're doing differently from a lot of distributed computing networks is we're taking an agent-first approach to a lot of the problems that have plagued distributed computing networks in the past, in particular for pricing and scheduling. I mentioned earlier that we have right now an intermediary node called a solver between clients and compute nodes that matches them. There is an alternative, which is that clients and compute nodes negotiate with each other directly. And there was a lot of fascinating research on this back in the 90s that is currently being resurrected slowly because it wasn't really applicable for a very, very long time. But now we have the relevant technology to actually start using this research from like 20, 30 years ago. We are taking an agent-first approach to pricing and scheduling. I don't want to say much more than that, so I'll just say watch out for that. Another thing that I want to mention are that we're building kind of a coordination layer for multi-agent systems. So this is the classic example I give. You can imagine that you're overlooking. So you go through right now in the Bay Area. So you can imagine that you're overlooking, let's say, San Francisco. From actually no, there's like almost no traffic in San Francisco. It's a terrible example. So I'm in the New York City area. So imagine you're like overlooking Manhattan from above, and you have all of these cars and people and trucks and etc. trying to get from point A to point B. And so they all go on Google Maps, and Google Maps gives them the shortest path algorithm, and everybody just goes to where they're trying to go according to what Google Maps told them to do. Okay, and so now imagine that you are overlooking Manhattan, but now you're in God mode, and you can run some optimization algorithm that can tell people like when to go and where to go and how to go. And so the average travel time in the first case, when everybody's like out for themselves, and the average travel time, and the ratio of that to the average travel time in the optimized case is called the price of anarchy. What we're building our coordination layers for taking environments like these and driving the price of anarchy down to 1, so that agents acting in a rational utility maximizing manner will in fact converge to a kind of will go towards a more optimal solution in general for the whole system. And so for in the car example, you can imagine reducing traffic, which like reduces emissions and has mental health benefits. And so it has all these benefits. And so how do nodes get rewarded? Well, you can imagine if you're willing to leave like half an hour later, or you're willing to take this other route, you get like more tokens, for example. And so you effectively get tokens for reducing emissions and reducing travel time and reducing mental health stress because of traffic and so on and so forth. There's all these benefits to it. And so what we're building kind of, let's say we have stuff in development, let's say that we're building basically to create coordination layers for decentralized intelligence.
Yeah, I really like that analogy about the traffic. That just gave me another question. How long does it take on average for like a client's job to be completed?
Oh, it depends on the job. So I think right now we have our stable diffusion is like really, really fast. That was like one of our first examples. I think, God, we might have like under 10 seconds or something like this. But it depends because jobs can be like, a small fraction of a second on the CPU, or it could be some kind of like simulation on a GPU that takes ages. So it really depends entirely on the job description.
Got it. Cool. Well, I think that about wraps it up for us.
Yeah, thank you so much for joining us. We really enjoyed learning more about CoopHive. And yeah, we'll see you at Demo Day.
Yeah, thank you so much. This was great. And yeah, looking forward to it.
That was Levi Ribola from CoopHive. We were your hosts, Tiffany Liu and Brent Friedman. Make sure to follow us to stay updated on our upcoming episodes and to continue exploring the cutting edge Berkeley Blockchain Accelerator.